In this section, our goal is to represent any infinitely differentiable function as a power series. And these two series are going to have special names, a Maclaurin series and a Taylor series. So the question that we want to answer is, how can we find a series representation of an arbitrary function? Let's analyze the function f of x equals e to the x. Our goal is to have a series, so we will start here. If f of x is equal to e to the x, then we want a function of the form f of x equals c naught plus c1x plus c2x squared plus c3x cubed, and so forth, or as an infinite sum. So the idea then is building on what we did with linear approximations. So with a linear approximation, we made sure that the function at the center was equal to the linear approximation at that point, and that their first derivatives, or they had the same slope at those points. So we can build that idea. So let's center our series at x equal to 0. And if we plug that in, we'll notice something very interesting happens. We get e to the 0 is equal to c0 plus c1 times 0 plus c2 times 0 plus all of the other ones, c2 0 squared, are going to have a factor of 0. So anything times 0 is equal to 0. So then e to the 0 is 1. That gives us 1 is equal to c naught. So then we would have our series would be e to the x is equal to 1 plus c1x plus c2x squared plus c3x cubed, and so forth. Well, if we want to make sure they have the same slope, we would take the derivative of both sides. And evaluate at x equals 0. So the derivative of e to the x is e to the x, the derivative of a constant 1 is 0, and the derivative of c1x is c1. The derivative of c2x squared is 2c2x, and the derivative of c3x cubed is going to be 3c3x squared plus ... on forever. And if we evaluate this at 0 once again, we get e to the 0 is equal to c1 plus 2c2 times 0 plus 3c3 times 0 squared. And as we see once again, we're going to have all of the higher ordered terms are going to have a factor of 0, and 0 times anything is 0. So we get 1 is equal to c1. So then that gives us e to the x is equal to 1 plus, and now we have 1 times x plus c2x squared plus c3x cubed plus on forever. And let's keep on going. So now, if we take two derivatives, the derivative of e to the x is going to be e to the x still. So we have e to the x is equal to 0, and the derivative of x is 1, plus 2c2x plus 3 c3x squared plus on forever. Now we take another derivative, e to the x. Derivative of a constant is 0. We get 2c2 plus, I'm going to write it out this way, 3 times 2 times 3 c3x plus ... on forever. We get this, and if we evaluate it 0 again, we get 1 plus 2c2 plus 3 times 2 times c3 times 0, and once again, all of the higher ordered terms are going to have a factor of 0. So then this leaves us with the equation 1 is equal to 2c2. And if we divide by 2 and divide by 2, that gives us that c2 is equal to 1/2. So now we have e to the x is equal to 1 plus x plus 1/2 x squared plus c3x cubed plus dot 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 on forever. And if we take a few derivatives, so we know from this line that the second derivative of e to the x was 2c2. So if we take another derivative, our third, we're going to get e to the x. The derivative of a constant is 0 is going to give us 3 times 2 times 1 times c3 plus we would have had 4 times 3 times 2 times c4x plus our higher ordered terms. And if we evaluate that at 0 once again, we get 3 times 2 times 1, which I'm going to write as 3 factorial c3, plus 4 times 3 times 2 times c4 times 0. And once again, all of our higher order terms are going to be 0. So if I divide by 3 factorial and 3 factorial, I get that c3 is 1 over 3 factorial. And so then we would have e to the x is equal to 1 plus x plus 1/2, or 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus dot 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 on forever. And if we keep doing this, we may be able to guess a pattern, and it turns out it's true that e to the x is equal to the sum as n goes from 0 to infinity of x to the n over n factorial. It turns out that in general, we have the following. The coefficients of the Maclaurin series are given by c sub n is equal to the nth derivative evaluated at 0 divided by n factorial. And we can use this to come up with the c sub n for any series. Alright, so let's take a look at our next example. So let's find the Maclaurin series for f of x equals 2 sine x. So to find our coefficients, if we use n equals 0, we have that c sub 0 is equal to the 0th derivative, or the function evaluated at 0. So that would be the sine of 0 divided by 0 factorial. Sine of 0 is 0, and 0 factorial is 1, so we get 0. And then for n equals 1, c sub 1 would be the derivative of sine, which is cosine. So we have the cosine of 0 over 1 factorial, which is 1 over 1, which equals 1. For n equals 2, we get c sub 2, and that would be, so we had the derivative of sine was cosine. The derivative of cosine is negative sine, so that's going to be the negative sine of 0 over 2 factorial, which is negative 0 over 2, which is 0. For n equals 3, we would have c sub 3 equals, the derivative of negative sine is negative cosine of 0 over 3 factorial. Cosine of 0 is 1, so that's negative 1 over 3 factorial, so that's going to be negative 1/6. And we keep going. And we have n equals 4. We have c sub 4. The derivative of negative cosine is back to positive sine. And that would give us sine of 0 over 4 factorial. And the sine of 0 is 0 over 4 factorial is 24. That gives us 0. But we'll also notice that we've come full cycle. And we have the property that for sine and cosine, the nth plus 4 derivative of x is equal to the nth derivative. So every 4 derivatives, it cycles. So we're going to get back to what we had. So then we can use our formula then. C sub n is the nth derivative evaluated at 0 over n factorial. But we noticed we have this pattern. We have 0, 1, 0, negative 1. 0, 1, 0, negative 1. So our pattern for sine is going to look like this. So we have n equals 0, n equals 1, n equals 2, n equals 3. And this is our pattern for sine. We're going to have 0, 1, 0, negative 1, and we're going to cycle. So then it looks like we're going to skip all of the odd numbers. So odd c sub n's equals 0. Or I mean even c sub n's. So we really only want to count the odd numbers. So then that means what we're going to have is c to the 2n plus 1 is going to be equal to negative 1 to the n plus 1 all over 2n plus 1 factorial. And if we check this, if we plug in 0, we get, this one should be just an n. If we plug in 0, we get 1 over 1 factorial. If we plug in 1, that's going to be 2 times 1 is 2 plus 1 is 3. So that would give us c sub 3 is equal to negative 1 over 3 factorial, which is what we got, negative 1 over 3 factorial and so forth. So we found our pattern for our c sub n's. So then the Maclaurin series for sine x would be the sum as n goes from 0 to infinity of negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And that would generate our Maclaurin series for x. All right, it's now your turn, so please go ahead and do the same thing. It's going to be really similar because sine and cosine have that same derivative pattern. You're going to have to be a little bit careful and move our pattern around a little bit and see what we get. All right, so the derivative pattern for cosine, so let's take a look. So we have n equals 0, n equals 1, n equals 2, and n equals 3. So cosine of 0 is 1. The derivative of cosine is negative sine. Negative sine of 0 is negative 0. And then at 2, we're going to have negative cosine, so we're going to get negative 1. And then at and then we're going to get sine, and sine is going to have 0, and then we're going to cycle back around. So then for each of these, we're going to have this same pattern. So this is going to be x to the 0, x to the 1, x squared, x cubed, and then for 4, 5, 6, and 7, we're going to get the same pattern. We're going to have 1, 0, negative 1, 0, and then we have x to the 7th, or no, x to the 7th left, x to the 4th, x to the 5th, x to the 6th, and x to the 7th. So then if we look at the non-zero coefficients, that's going to be here, 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 here. So it looks like all of the odd coefficients this time are going to be 0, and all of the even ones are going to be not 0. So we have 1 minus x squared, and this is going to be over 2 factorial, plus positive 1 over 4 factorial x to the 4th, minus 1 over 6 factorial x to the 6th. So plus, and if we write this out, we're going to have something that looks like this. N equals 0 to infinity of x to the 2n. Alright, I forgot my alternating sign. Negative 1 to the n, x to the 2n, all over 2n factorial. And that would be our Maclaurin series for cosine. So the Maclaurin series is a special case of a more general series called a Taylor series. So the Maclaurin series is always centered at x equals 0. But as we discovered with a linear approximation, sometimes it's better to move the center to somewhere else. So we would do exactly that by using function composition and just shifting it to have center A. And if you'll notice, this looks exactly like the Maclaurin series, but we have x replaced with x minus a, so that would shift the series from x equals 0 to having center x equals a. So we can do this directly. So now our center is here. We're still going to have this same pattern. So we have f of x equals sine x. F prime is going to be cosine x. F double prime of x is equal to negative sine x. And f triple prime of x is going to be negative cosine x. And then we're going to cycle back around once again. And if we evaluate at pi over 2, well, f of pi over 2 is the sine of pi over 2 is 1. The cosine of pi over 2 is 0. The negative sine of pi over 2 is negative 1. And the cosine of pi over 2 is still 0. So it looks like our pattern is going to be 1, 0, negative 1, 0, and then we're going to cycle back. So then for n equals 0, we're going to have 1 over 0 factorial x to the 0. For n equals 1, we're going to have 0 over 1 factorial x to the 1. For n equals 2, we're going to have 0 over 2 factorial x squared. For n equals 3, we're going to have, for n equals 2, we should have had negative 1. That's my bad. And for n equals 3, we get 0 over 3 factorial x cubed. And then we start recycling. So for n equals 4, n equals 5, n equals 6, and n equals 7, we're going to have 1 over 4 factorial x to the 4th, 1 over 5 factorial x to the, or 0 over 5 factorial x to the 5th, negative 1 over 6 factorial x to the 6th, and negative 0 over 7 factorial x to the 7th. So this time it looks like the even numbers have non-zero. So our c sub n's are going to be negative 1 to the n, x to the n, all over n factorial. Or, sorry, 2n. Factorial. And so that would give us that the Taylor series for this at our center, it's x minus pi over 2 to the 2n. Because I'm using this formula right here, and that is my a. So I had originally written x, but it should be x minus pi over 2 to the 2n. So then that would give us that sine x would be equal to, the sum as n goes from 0 to infinity, of negative 1 to the n times x minus pi over 2 to the 2n all over 2n factorial. All right, so the next one is a U try for you guys. So go ahead and find the Taylor series for f of x equals x to the 4th minus 4x cubed plus 6x squared minus 4x plus 1 at x equals 1. So then we would need to find f of 1 would be 1 to the 4th minus 4 times 1 cubed plus 6 times 1 squared minus 4 times 1 plus 1. So that's 1 minus 4 plus 6 minus 4 plus 1, which is going to give us negative 8 plus 8, which gives us 0. So f of 1 gives us 0. And we take our derivative, so then f prime would be 4x cubed minus 12x squared plus 12x minus 4, and we evaluate it at 1. That gives us 4 times 1 cubed minus 12 times 1 squared plus 12 times 1 minus 4. So 4 minus 12 plus 12 minus 4, once again, is going to give us 0. So this gives us, sorry I didn't write it out explicitly, C0 is 0 over 0 factorial. C1 is 0 over 1 factorial. So now we take another derivative, f double prime, and we get 12x squared minus 24x plus 12, and we evaluate that at 0, or at 1, sorry. Gives us 12 times 1 squared minus 24 times 1 plus 12. So 12 minus 24 plus 12 gives us 0. So now we have c sub 2 is 0 over 2 factorial. And we do f triple prime. So that's going to be 24x minus 24. So f triple prime of 1 is 24 times 1 minus 24, which gives us 0 once again. So now we get c sub 3 is 0 over 3 factorial. So c sub 3 is 0. Finally, we take the fourth derivative, and we get 24. And the fourth derivative, evaluated at 1, is going to be 24. So that gives us that c sub 4 is equal to 24 over 4 factorial. Well, 4 factorial is 24, so c sub 4 turns out to be 1. And then finally, for our next derivative, the fifth derivative, the derivative of a constant is 0. And in fact, all of the derivatives after that are going to be 0. So c sub n is going to be equal to 0 over n factorial, which is 0 for n greater than or equal to 5. So in this Taylor series, C0, C1, C2, C3 are all 0, C4 is 1, and then the rest of them are 0. So what does that tell us? Well, f of x was equal to x to the fourth minus 4x cubed plus 6x squared minus 4x plus 1. Well, this is equal to 0 times x minus 1 plus 0 times x minus 1 squared plus 0 times x minus 1 cubed plus 1 times x minus 1 to the fourth plus 0 times x minus 1 to the fifth. And in fact, all of the other terms are going to be 0 as well. So then this tells us that it's equal to just this term. So x to the fourth minus 4x cubed plus 6x squared minus 4x plus 1 is equal to x minus 1 to the fourth power. And that would be its Taylor series centered at 1. All right. The next thing we want to talk about is Taylor's inequality. So Taylor's inequality says that if the absolute value of the nth plus 1 derivative is bounded by m for all x in some interval centered at a with radius d, then the remainder of the Taylor series satisfies it is less than m over n plus 1 factorial times the absolute value of x minus a to the n plus 1 for all x in that interval. And it's worth noting, and we're going to need this, that for every real number x, the limit as n goes to the infinity of x to the n over n factorial is going to be 0. All right, we want to prove that the series, that e to the x is equal to the sum of its Taylor series at 0, or its Maclaurin series. The sum as n goes from 0 to infinity of x to the n over n factorial. So what we need to show is that the remainder goes to 0 regardless. So we have that f of x is equal to e to the x. Well, this one is fortunate because the nth derivative of e to the x is easy to take because the derivative of e to the x is always e to the x. So we know then that the nth derivative will always be e to the x. And if we are on some interval, we know we're centered at a equals 0. And if we're on an interval from negative d to d, it's going to look something like this. And if we have the exponential function we know is always increasing. So it's going to have its maximum value at the end of that endpoint at the point d, e to the d. And this is going to be the absolute max on that interval. So then we would know that the nth derivative, since e to the x is always, the derivative of e to the x is always e to the x, that the nth derivative is always going to be less than e to the d, where d is the endpoint for that interval. So for all x in the interval negative d to d. So then, using Taylor's inequality, we have the absolute value of the remainder is less than or equal to m over n minus 1 factorial. So we're going to have e to the d over n, I think I said minus 1, it's n plus 1 factorial times x minus a, but in this case our a is 0, so that's x minus 0 to the n plus 1. So then that is equal to e to the d times the absolute value of x to the n all over n plus 1 factorial. So now we take the limit as n goes to infinity of the remainder, which is going to be equal to the limit, or less than or equal to the limit as n goes to infinity of e to the d, absolute value of x to the n, all over n plus 1 factorial. Well, e to the d is a constant, so it comes out of the limit, and we have the limit as n goes to infinity of x to the n all over n plus 1 factorial. So if you applied L'Hopital's rule n times, you would eventually get a constant. You'd have n times n minus 1 times n minus 2 times n minus 3 all the way down to this, and you would finally end up with a constant, or 1 over n plus 1, but this limit goes to 0. You can also note that from the fact that x to the n over n factorial is equal to 0, and we could rewrite this as the absolute value of x to the n all over n plus 1 times x to the n, and we'll get what we need. So if that limit is 0, that's e to the d times 0, which is 0. So that means the remainder of that series goes to 0, as n goes to infinity, which means the error goes to 0, which means the series converges to what we wish it to converge to, which is e to the x. So example 5, find the Taylor series for f of x equals e to the negative x squared centered at a equals to 0. So, as we learned about with power series in 11.9, we do not have to build all of these series from scratch. In fact, we already know now that we have a Taylor series for e to the x. In fact, we know that the Taylor series for e to the x is the sum as n goes from 0 to infinity of x to the n all over n factorial. Well, this right here is e to the x composed with negative x squared. So if we say g of x is equal to e to the x is equal to this, then f of x would be equal to g evaluated at negative x squared. Because it's the function composition of e to the x with negative x squared. So if we replace all of our x's in g of x with that, indeed we're going to get e to the negative x squared, but if we do that also in the Maclaurin series, we're going to get negative x squared all over n factorial. So if we clean this up a little bit, we can write negative x squared as negative 1 times x squared, which would be negative 1 to the n times x squared to the n all over n factorial, which would be the sum as n goes from 0 to infinity of negative 1 to the n x to the 2n all over n factorial. And that would be the Taylor series for e to the negative x squared centered at a equals to 0. All right, the next one is a U-try for you guys. So find the Taylor series for f of x equals x squared sine x squared centered at a equals 0. So let's start with our g of x is equal to, and we'll have g of x be sine x, and we know that the Taylor series centered at 0 for sine x is negative 1 to the n x to the 2n plus 1 all over 2n plus 1 factorial. So then, if this is our sine x, we have two things that are happening. So this is composition with x squared, and out in front we have an x squared, and this is multiplication by x squared. So then f of x would be equal to x squared times our g of x, but g of x is composed with x squared as well. So then that would be the same as x squared times the sum as n goes from 0 to infinity of negative 1 to the n, and then we're going to have x squared raised to the 2n plus 1 all over 2n plus 1 factorial. So we clean this up a little bit. We have x squared times the sum as n goes from 0 to infinity of negative 1 to the n. X squared to the 2n plus 1 is x to the 4n plus 2 all over 2n plus 1 factorial. And then if we send that into our series, we finally get the sum as n equals 0 to infinity of negative 1 to the n, x to the 4n plus 4 all over 2n plus 1 factorial. So then that series represents x squared sine of x squared centered at a equals to 0. All right. So example the last is how many terms of the Taylor series are needed to approximate sine of 17 to 6 decimal places of accuracy. So we're going to want to use Taylor's remainder theorem, but we need to remember we always have to have things in radians. So the first thing we need to do is convert 17 degrees to radians. So if we have 17 degrees over 1, we have pi radians, so pi over 180 degrees. And our degrees reduce out, and that gives us 17 pi divided by 108. So 17 degrees is the same as 17 pi over 180 radians. And we need to use Taylor's remainder theorem. So we have the absolute value of the remainder is less than or equal to m over n plus 1 factorial times x minus a to the n plus 1. And m is the maximum of our function. Well, since we're talking about sine, and we know that sine's derivatives are either sine or cosine, the nth derivative of sine or cosine is always sine or cosine. So that's going to be less than or equal to, or it's going to be equal to either the absolute value of sine x or the absolute value of cosine x. And both of those are less than or equal to 1 always. So that tells us that the nth derivative of sine is always less than or equal to 1. So putting all of this into our remainder formula, we get 1 over n plus 1 factorial. Our center is 0, and our x is going to be 17 pi over 180 raised to the n minus 1. Or to the n plus 1. So this is our remainder theorem, but we have to recall that the CNs were x to the 2n plus 1 all over 2n plus 1 factorial, because we had every other term equal to 0. So we are skipping all of the even terms when we do this. So we can then replace all of these terms, this is going to be equal to, we're going to replace our n with 2n plus 1. It's going to be 1 over 2n plus 1 is 2n plus 2. 17 pi over 180, and we're going to get the same thing, 2n plus 2. So now if we grab our calculator, we know our error has to be less than this. So we go y equals, and let's go ahead and put this in. So 1 over 2x plus 2 factorial, so we go math 4 times parenthesis alpha y equals 17 pi over 180 all raised to the 2x plus 2. Now we go second table. And we need our error to be less than, so we need less than 6 decimal places of accuracy. So it gives us these for our possible n values. So our remainder is going to be less than that. Just for sign in and see what we get. So we go alpha window, we grab our summation. And we have the sum as n goes from 0 to x of our fraction. We have -1 to the n all over 2n plus 1 factorial. Now times the 17 pi divided by 180, and all of that raised to the 2n plus 1. So now we look at our table and we get our sum and we see that our error goes down pretty quickly. And just to verify, let's go ahead and calculate the sine of 17 degrees so that we have the exact value, or not the exact value, but a decimal approximation. And we'll notice we were trying to find this accurate to 6 decimal places. And we notice that our error after 2 is to the -7th, and we get something that looks like this. So let's calculate the sum as n goes from 0 to 2 of our sum as n goes from 0 to 2 of our -1 to the n all over our 2n plus 1 factorial and times that 17 pi divided by 180 all raised to the 2n plus 1. And if we do the sum, we get 0.29223717. And we compare that to the sign of 17, 1, 2, 3, 4, 5, 6, 7 points of accuracy. And we saw that our error here was we wouldn't have enough at 1, but at 2 we finally made it to where we need to be. So we can approximate the sine 17 degrees using that.